Hello, everybody. Today I'm going to talk about tournament solutions. So imagine, for instance, a club of tennis players. So all of them played once and only once against one another. And you have the result of each pairwise comparison between the players. So for each pairwise comparison, you know which player of the two did win the duel. And the natural question that arises in such situations is there a good notion of who are the best player for a good meaning of best? So, of course, this has application in sports, also in voting and aggregation of preferences, because when you have a lot of voters giving their opinions about candidates, for each candidate, for each pair of candidates, you can look at the majority relation, which is there a majority of voters preferring one candidate over the other, or vice versa. You can have a look also at individual non-transitive preferences, like in psychology, and also multi-criteria decision, which look a bit like voting, but where the criteria for something are the equivalent of the voters, and the items on which you want to make a decision are the equivalent of the candidates. Okay. So this talk is mainly based on one reference, which is the first one, the book by Jean-François Laslier, which is called Tournament Solutions in Majority Voting. But now there is also a more recent reference, which is more up to date, of course, which is the chapter Tournament Solutions in the Handbook of Computational Social Choice. So first, I will cover the basic notions of the talk. Then I will present some miscellaneous solutions for this problem, and then a particular class of solutions that I will call game theoretic solutions, and then I will conclude. So a tournament T is given by a finite list of candidates and a complete antisymmetric and irreflexive relation on them. Another way of seeing that is simply to say that you have a complete graph and you choose an orientation for each edge of the graph. So this can be represented, for example, by the adjacency matrix. So here, for example, the candidate A beats candidates B and C. The candidate B beats the candidate C and D. The candidate C beats D and D beats A. You can also represent it as a typical graph representation. Here with the convention that when I put a circle like this, it means that all the edges that are outside of the circle are the same for the candidate that are in the circle. So here, for example, A beats both B and C, and both B and C beat D. And we will often use also another representation convention, which is to use the altitude of the candidates to say which one are the best, and represent only the arrows that are not that are from down to up. So here, for example, this representation is exactly the same tournament as the two first one. A beats B and C, and it would beat D, except the fact that we explicitly represented that D beats A. B beats C and D, and C beats D. So it's a compact way to represent a tournament by representing most of the edges only by the altitude on the picture, and putting only the edges that are against the natural altitude. Yes?
How did you choose A first?
That's an arbitrary choice. And in fact, here I have chosen the option that minimize the number of explicit arrows that I need to put. But yeah, you can see it as an arbitrary choice. So a tournament solution is a function whose input is a tournament, and the output morally is a subset of the candidates. But to be a bit more clever, we will say that the output is a sub-tournament of the first tournament. And that will be very useful to formalize it like this, because then we will be able to compose tournament solutions. So when you apply a first tournament solutions, you get a sub-tournament, and if you want, you can apply another tournament solution to the sub-tournament. So we will always require that the tournament solution is neutral in the sense that it respects the symmetry of the graph. So if you have three candidates, for example, that are in a complete symmetric pattern, then the tournament solution must choose all the three candidates or neither of them. And we will also always assume that a tournament solution must select the Condorcet winner and only the Condorcet winner when there is one. When I say the Condorcet winner, it would mean a vertex of the graph that beats all the other vertices. So formally here, for example, I take the same example as before. We have a tournament here, and a solution could be to select A, B, and D, for example. So theoretically, we should formally we should write that is the tournament restricted to A, B, and D, but in a more loose writing, we will simply write that the solution is A, B, and D. As a remark, all the tournament solutions give the same output when there are 1, 2, or 3 candidates. Do you see why it is true? So the output is a sub-tournament, but morally it amounts to choosing a subset of candidates, which can be one candidate or more candidates. But so the only assumption is that when there is a Condorcet winner, so when a candidate wins all its pairwise comparison, this candidate should win. And the second requirement is that the solution should be neutral. So when there is only one candidate, why is there only one possibility? Because of which possibility, which property? Because she is the Condorcet winner. She wins her 0 pairwise comparison, so she's the Condorcet winner. She must win. When there are 2 candidates, same thing. There is always a Condorcet winner. When there are 3 candidates, yes, there are 2 cases.
Neutrality takes over.
Yeah. So either when A beats B, B beats C, and C beats A. And in that case, the situation is symmetric, and then the solution must elect A, B, and C necessarily because of the neutrality assumption. And if you're not in that case, in fact, one candidate wins 2 pairwise comparison, and in that case, she's the Condorcet winner, and she must be the only winner. So there's no question when there are 1, 2, or 3 candidates, all the tournament solutions will give the same output. So now let's see an example of a tournament solution that will work for any size of tournament. It's called the top cycle. So the top cycle is the smallest subset of candidates such that all the members of this subset win against all the non-members of this subset. So another way to see that is that you decompose the graph in strongly connected components, and you take the maximal strongly connected component, because these people will have a path that will go from one to another, so you cannot remove candidates from this, and they win again against all the other candidates because it's the maximal strongly connected component. So that in voting, this is called the top cycle. So of course it's neutral because I introduced nothing particular about one candidate or the other. And when there is a Condorcet winner, is also the maximal strongly connected component because she wins against all the other candidates. So it is indeed a tournament solution according to the definition that we have. So let's take some example. So I will take the same example as in the beginning. So here, A beats B, B beats C, C beats D, and D beats A. So in fact, there is only one strongly connected component in the graph. So the top cycle is ABCD. You cannot remove one candidate, in fact, because if A is in the top cycle, then D needs to be also, because D wins against A. Then C needs to be in the top cycle. Then B needs to be in the top cycle. So everybody must be in it. Another example of tournament would be this one. So let's have a look at what it means exactly. So here the altitude tells us that A, B, and C win against D by convention. And we have here a cycle between A, B, C, and back to A. Okay. So here the top cycle would be A, B, C, and you can say, okay, D is not good. One of the problems with the top cycle is that usually it's relatively big. So you will put many candidates in that tournament solution, except of course when there is a Condorcet winner. And all the other tournament solutions that we will talk about today are in fact included in the top cycle. So we can do something that is smaller in general. Now let's talk about the axiomatic properties that a tournament solution may meet or not meet. For example, we will say that a solution is monotonous if, so imagine you have a tournament and you have one of the winners is A. Imagine that you reverse a pairwise comparison of A that was a defeat to make it a victory. So you have a new tournament, a transformed tournament, when you improve, in fact, the situation of A, because a pairwise comparison that was a defeat now is a victory. And you assume that A was one of the winners in your tournament solution in the initial tournament. Then, of course, you would like that in the new tournament, since the situation is improved for A, you want him to still be in the winners. So that's the property of monotonicity. That's exactly what you want. Also, you would like to have the property of the independence of the losers, so more precisely, the independence of the matches between losers. So, for example, imagine that you have a tournament solutions, and let's say that A, B, C are the winners, and D and E are the losers. Okay, you change your tournament by modifying the pairwise comparison between D and E, who are some losers. You would like to say that shouldn't change much the results. A, B, C should still be considered better than D and E anyway. Sorry. There is also another property called the strong superset property, which is that if you remove one of the losers, the result should be the same. And actually, if you have monotonicity and the strong superset property, you can show that it implies the independence of losers. We have also the Eiserman property, which is that if you remove a loser, then you may diminish the set of winners, but that's the only thing that can happen. And later we will see an example giving an intuitive justification of this property. I guess so. Of course, this is weaker than the strong superset property, because the strong superset property, we say when we remove a loser, it shouldn't change the winner. Eiserman is only that if we remove a loser, the new set of winners can be included in the old set of winners. And the idempotency is a very natural property, which is to say that when you apply the same tournament solutions twice, you shouldn't change anything. For example, with the top cycle, when you apply the solution, the first one, you only keep the maximal strongly connected component. Now you have a new tournament with only the winners. If you apply this tournament solution again, you will say, okay, the winners stay the same. I will not restrict again the set of winners by applying the same solution again. That's a very, very natural property. And actually, and we will come back to that later, if you have a solution that is not idempotent, you are very tempted to iterate the solution. Because if you can continue to restrict the number of winners, it's very interesting to use it as a tie-breaking rule for itself, in fact. And now the composition consistency. So it's a bit complicated to formalize, but it's a very natural property. So imagine that you have a tournament that is decomposable in the sense that you have, for example, a tournament between some big projects, A, B, C, and D, okay? And for example, all the projects A are considered better than all the projects B, all the projects B are considered better than all the projects D, and so on. But you also have sub-tournaments between variants of A and sub-tournaments between variants of B, okay? And the composition consistency will say that if the winners of the tournament of this shape with A, B, C, D is, for example, A and B, then the winners of the big tournaments with all the variants of A and all the variants of B should be the winners of the tournament of the AIs and the winners of the tournaments of the BJs. Okay. Okay, so now let's see that on an example. Let's see that the top cycle is not composition consistent. Okay, so here we have this tournament, this big tournament that is a composition. In fact, we have first a big tournament between A, B, and C, and D, which is a tournament between 3 options. And we have a small tournament between B and C, where we learn that, in fact, B is better than C. Okay, but from the point of view of the rest of the world, B and C are equivalent. Okay. So if you look at the winner of the small tournament between B and C, it's B, of course, because it's the Condorcet winner of this small tournament with 2 candidates. If you have a look at the winner of the tournament with 3 elements, so A, B/C, and D. So it's who wins this tournament? Everybody, thank you, because it's a tournament with 3 options and with a cycle. And if the top cycle was composition consistent, then we should elect A, D, and the winners of that sub-tournament, which is B. So the winners should be A, B, and D, in fact. And with the top cycle, it's not the case. With the top cycle, in fact, the winners are everybody. So that proves that the top cycle is not composition consistent. And actually, on that particular example, we really would like to have A, B, and D. Because for the sub-tournament, it's necessarily B. For the tournament with the 3 cycle, it's necessarily everybody. So if we want a tournament solution to be composition consistent, in that case, it's necessary that it elects A, B, and D, which is not the case for the top cycle. But for the rest, the top cycle is not so bad. Actually, it's monotone. It meets the strong superset property, which implies that it respects the independence of losers, and which also implies that it meets the Eiserman property and the idempotency. So our goal ideally would be to select also few candidates, because if if in your tournament solution you say, okay, I elect the Condorcet winner if there is one, and everybody if there is no Condorcet winner, it's not very interesting, in fact. So when we have two tournament solutions, we will say that S is finer than S prime. Sorry, the prime is missing here. If for any tournaments, in fact, S outputs something that is inside the solution of S prime. And ideally, we would like to have a tournament solution that has all the good properties that we mentioned, but that is also very fine in the sense that it selects few candidates. So let's talk about some miscellaneous solutions. So first, a very simple one is the Copeland solution. So the idea is simply to say that we will elect the candidates that have most victories. So here in my example, A has 2 victories, B also, C and D have 1 victory, and the Copeland winners are A and B. Alors, of course, it's neutral because I didn't mention anything that specializes on a particular candidate. And also it elects the Condorcet winner when there is one, because when there is a Condorcet winner, the Condorcet winner has m-1 victories, and she's the only one to have that many victories. One possible model to justify this solution is to imagine that there is a ground truth, which is a relation of strength between the candidates, and that each match is an independent observation, and we get a false result with probability p smaller than 1/2. And in that case, the maximum likelihood solutions to try to guess who is the best candidate in the ground truth are the Copeland winners. So about the axiomatic properties of the Copeland solution, it's monotone, of course, because if you revert a victory of a winner, she will have less victories, and no, she will no, the opposite. If you revert a defeat of a winner and make it a victory, in fact, she will still be a winner, and in fact, she will even become the unique winner. So it's monotone. It's not independent of losers, because here, for example, if D defeated C, then D would have 2 victories, and she would become a winner. So if you change the pairwise comparisons between the 2 losers, in fact, you change the set of winners. So it's not independent of the losers, of the matches between the losers. Also, if you remove the candidate C, then you will have a typical cycle between 3 candidates, and the winners will be A, B, and D. So it does not meet the strong superset property, because if it would, then when you remove a candidate, you should keep the same set of winners, which is A, B. Here you add 1, which is D. And it's not even Eiserman, because Eiserman would say if you remove candidate C, the new set of winners should be included in the old set of winners. You are not allowed to add somebody who was a loser. And finally, if you apply the Copeland solution, you say, okay, the winners are A and B. Now let's try to tie break them by using Copeland again. If you do that, in fact, A has a victory against B. So the new Copeland score of A is 1 and the new Copeland score of B is 0. And so the Copeland winner will be A. So in fact, when you use the Copeland solution twice, you can restrict even more the number of winners. It's not idempotent. What did I say? Yes, it's about composition consistency. So here it's essentially the same kind of problem as for the top cycle. I will skip the details.
Yeah. When you consider the group B and C, you do the sum of the victories of B and C.
Sorry?
The Copeland solution with this case in which B and C are together.
Yes.
In that case, the cluster BNC has
So-
sum of victories.
Okay, so here, in fact, the rightmost figure is just a conventional representation of the adjacency matrix. Now, what is important is the adjacency matrix.
Okay.
So here the adjacency matrix is here. So so B has two victories. A has two victories, for example, one against B and one against C.
Okay.
Okay, so the figure is just a convenient representation of the adjacency matrix. It should not have more meaning than that. Mm. Questions, comment or question? Yes, of course. So the computational complexity of the Copeland solution is essentially to read the matrix. So it's n square. And for the other one, I think it should be something like Floyd-Marshall or something like that. So maybe n to the cube, something like that. It's relatively easy to compute anyway.
Let's come back to the composition consistency as was mentioned.
Of which one? Of Copeland?
Yeah.
Yes.
Here, when you look at the great tournament, you called it, you're assuming that BC scores 1. You're not weighting that score by the size of the tournament. You could say BC beats D,
Yes.
but since they're a bigger set, that victory is worth 2 rather than 1. When you sum your scores.
No, once again, just so the clustering that I used is just a convenient representation, especially to see what the composition consistency will entail.
Yeah, but you don't look at that cluster,
No,
the size in composition consistency when you do the Copeland.
no. In
You're
fact,
not doing Copeland on the
yes,
tournament.
yeah. Really, I insist on the right. It's just a convenient representation to visualize what the composition consistency will ask us. But really, just think of the adjacency matrix. You really have 4 vertices and the edges that are given here.
The circle is not part of the model, it's just for our eyes.
Exactly.
For composition consistency, you do have a major tournament where you're
Yes.
a solution to that major tournament.
Yes.
And in that major tournament, BC is considered as one player. And you don't weigh its score by its size.
Yes, exactly.
Yeah, that was the
Exactly. Yes, exactly. Yes, exactly.
Because you could have the model where
Yes.
in the major tournament,
Yes.
you weigh them.
Yes, but in fact, just to be clear, you could have a case where you have your tournament, and you have several representations, several possible clustering like the one on the right, and for each of these possible clustering, you would need to respect composition consistency. Okay. So for the composition consistency, the thing is that each time you have a decomposition like this, you should meet the composition requirement. Sorry, there is a message on the chat. Yes, something like that. Okay, so let's go. So now the Slater solution. So here it's also a maximum likelihood solution. So imagine that there is a true relation of strength between the candidates. So you have a full order, which is the ground truth that you are looking for. Okay. And each match is an independent observation. So we get a false result with probability p less than 0. And we want to find all the order that will maximize the likelihood. And that amounts to reorganize the columns and the rows of the matrix to maximize the number of one coefficient above the diagonal, or to minimize the number of one coefficient below the diagonal. And the Slater winner will be a top element of this order. So here, for example, and that also answers about the question from Emma before, there is only one optimal order for this, the order A, B, C, D, because only D is an exception to the order ABCD. In fact, only the pairwise comparison between D and A is an exception to the order ABCD. So here in that example, the Slater winner would be A. Sorry. Unfortunately, the Slater solution does not have very good properties. It's only monotone, but it does not mean does not meet any one of the other axiomatic properties. I will skip the Markov solution, but essentially, yeah, I can say a few words. Essentially, the idea of the Markov solution is that you start by a node, and then you simply follow links to somebody who beats you at random. So you choose among the candidates that are stronger than you. You go to one, and then you do a Markov chain like this. And then you look at the candidates who have the maximal probability at equilibrium of that Markov chain. Okay, so now the game theory solutions. So all these solutions come from the idea that a tournament can be seen like the matrix of a two-player game. Okay. So I can imagine a game between Remy and me, for example. Remy needs to choose a candidate. I need to choose another candidate. So simultaneously, we will choose a candidate and we will look at the matrix to win. So for example, if I choose the candidate A and Remy chooses the candidate B, then A wins against B, I'm the winner. I get 1 point, okay? So now the question are, what are the good strategies in that game? And in fact, my example is precisely the matrix of a famous game. Okay, so when you have a two-player game that is deterministic, a zero-sum deterministic two-player game, you can represent it as a matrix. Okay, so here it just means that if one player chooses strategy A and the other player chooses strategy B, for example, then the one choosing A gets to win.
And you
Okay.
know this matrix beforehand, like
Okay.
two players know the matrix.
Exactly.
Okay.
Exactly.
Know what the other thing.
Okay, but we don't know in advance
Yeah,
what the other will play. So a very famous example of that is rock, paper, scissors. Okay, so if here, for example, if I remove B or C, let's say that I just take A, C, and D, for example. So forget about B. Okay, A beats C, C beats D, D beats A. That's exactly the situation of rock, papers, and scissors. Okay. Here we have a small thing in addition, which is the well. I don't know if you know the variant of rock, paper, scissors with the well. So I will try not to mess up, but the paper wins against the well because it covers the well. The scissors fall in the well, and which one did I forget? And the rock falls also into the well. Okay. And in particular, the well is strictly stronger than the rock because it has the same advantage against the scissors. It beats the scissors like the rock. It is beaten by the paper like the rock. But in addition, the well is better than the rock. So when you want to choose rock, it's really stupid. You should choose the well instead because it wins exactly the same situation. But in addition, it also wins against the rock. So here it's exactly that situation. And in fact, here B and C are respectively the well and the rock. Okay. So now that we have transformed our tournament into a game, in fact, we can use all the usual notion of game theory. For example, the uncovered set. So here in my example, a covered strategy is a strategy that is strictly less good than strictly worse than another one. So here, for example, rock is strictly worse than the well. So it's covered by the strategy well. Okay. So we will keep only the uncovered strategy. So here it will amount to keep only A, B, and D. That's exactly what the uncovered set does. And that's a tournament solution, in fact. Why? It's neutral, easy. And if there is a Condorcet winner, so if you have a candidate that is a Condorcet winner in a tournament, what happens with the corresponding strategy in the game that you, so you transform your tournament into a game, the candidate is transformed into a strategy. What is the particular property of that strategy in the game if the candidate is a Condorcet winner? He always wins, yeah. So it's a winning strategy, it's a deterministic winning strategy. And in particular, all the other strategies are covered by this strategy. So in that case, the Condorcet winner is the only element of the uncovered set. Okay, I already told everybody everything, sorry. The main problem with the uncovered set, in fact, is that it's not idempotent. So I will not show it now. But what you can do is to iterate, since it's not in the idempotent, you can iterate the uncovered set. So you can remove strategies until you have only uncovered strategy. So let's have a look at that tournament that is a bit more complicated. So we have a top cycle here with A, B, and C. These guys are better than A prime, who is better than B prime, who is better than C prime, except for the fact that A prime beats A, B prime beats B, and C prime beats C. Okay, so that's just two representations of the same thing. Let's go. So let's observe that C prime is covered by A, because C prime wins only against C, but A already does that. So if you want to play C prime, that's stupid. Just play A instead. So the uncovered, and in fact, you could check that it's the only covered strategy. So now the uncovered set is A, B, C, A prime, B prime. But now you can observe that B prime wins only against B, and that C covers in fact B prime, because C wins against B, but also against A prime and B prime. And you can also observe why B prime was not uncovered before, because when C prime was there, in fact, B prime had the advantage of beating C prime, whereas C was not able to beat C prime. So that's why B prime is now in the uncovered set, but was not in the uncovered set before. So you can remove B prime. Now, you know the trick. So A prime now is covered by B, because A prime wins only against A. And finally, you have only ABC. And now you have a typical rock, paper, scissors configuration. So no strategy is uncovered, and you have finished. And so we will denote by UC infinity the fixed point of this process of removing the covered strategies.
When you remove at each step, you should remove all the cover strategy. Or
Yes.
if you remove one by
Yes.
one, then you get somewhere.
Yes, but in fact, I think that it's equivalent. Yes. Yes.
Out of all your properties on the previous slide, which of them are stable by composition?
In general, not. But what is easier to look is that is the final iteration, infinite iteration, meets the properties or not for this particular case. Okay. So great example. So let's go back. The uncovered set is monotone. Okay, that's just for the one iteration of removing the cover strategies. Unfortunately, when you iterate it until completion, it's not monotonous anymore. So there is a small example here. I see that we are short on time, so I will not I will not continue, but so unfortunately, the iterated uncovered set is not a very satisfying solution for this reason. Okay, now we can talk about the minimal covering sets. Okay, so here the idea is essentially the same, but what you want to do is to take the smallest set of strategies so that if you add another strategy, it's necessarily covered. So intuitively, that's what. So it's also a fixed point of removing the covered alternatives. Okay. But the problem is that when you start from all the strategies and you remove them little a little, sometimes you will not see that you can remove several of them in the same time, because when they are together, they are not covered. But if you remove them all, in fact, adding any one would be covered. Do I have an example? Here's the same example as before. No, it's not the same example as before. Okay, this is an example. So here my example is slightly different from before, because if you remember my previous example, here between A prime, B prime, and C prime, I had a clear order. So A prime was better than B prime, B prime was better than C prime. Okay, there was a full order on this 3-1. So it was relatively easy to remove them by one by removing first C prime, which was really the weakest of all, and then removing B prime, and then removing A prime. But in my new example, in fact, I have a cycle between the weak candidates. And in fact, none of them is covered. You can check that in the matrix, because there's no weakest candidate in some sense that you could obviously remove. But in fact, if you remove the 3 of them, you will see that, okay, so you only keep A, B, and C, for example. Now let's try to add A prime, just A prime. A prime would win only against A, not against B, not against C, not against herself. And B prime and C prime are not here anyway. Okay, we start from A, B, C. And so this A prime is covered by the strategy B, who wins against B and also against A prime. Okay, so ABC, if you have only ABC, you cannot add A prime because it's a covered strategy. And the situation is strictly symmetrical for B prime and C prime. So here you have a small set of uncovered strategies that you don't see if you just remove the cover strategy one by one. And this shows that the minimal covering set can be strictly included, in fact, in the iteration of removing the uncovered strategies. And that is the first solution that we see that has all the nice properties. So it's monotone, strong superset property, independence of losers, Eisenman independent, composition consistent, wonderful, wonderful solution. But in fact, we can do even better with the essential set. So when you have, so a basic result in game theory is that when you have a zero-sum game like this, there exist some winning strategies, some optimal strategies, for both players. So there are equilibriums in mixed strategies. So in fact, for rock, paper, scissors, for example, there is a unique equilibrium, which would be that I choose rock, paper, or scissors with probability 1/3, and Rémi does the same, in fact, because it's a symmetry, it's totally symmetric. And in fact, if I deviate from that probability distribution, then Rémi will be able to exploit this. For example, if I choose scissor more often, of course, Rémi will choose rock more often, and he will win more than half of the time. So that can be done in general. So the famous theorem is that there is always existence of such winning strategies, but in fact, in the particular case of a tournament, in fact, there is also unicity. There is a unique winning optimal strategy for player 1 and player 2. Okay. And since here the game is perfectly symmetrical, it will be in fact the same strategy for player 1 and player 2. And the essential set will be the support of the probability distribution given by that strategy. So if I take again my example of rock, paper, scissors, and well, the optimal strategy is to play well with probability 1/3, rock with probability 0. It's just stupid to play rock, and two other with probability 1/2. So here the essential set will say, okay, the winners are well, paper, and scissors. Okay, so A, B, and D in my example. That's what the essential set does. In that very simple example, in fact, it's exactly the same as the minimal covering set in that example. Okay, so here, if I take an example that is a bit more complicated, so with the usual convention that candidates that are higher are better than the ones that are lower. So here, for example, A is better than B, C, and D. But since we have explicit arrows from E to A and from F to A, then E and F beat A, and so on. So it's just, once again, two representations of the same thing. If you compute the optimal strategy, you will see, and here you just need to believe me, that the optimal strategy is to play everybody except F with different probabilities. So here the essential set is A, B, C, D, and E. So the question is, what is the minimal covering set? So the minimal covering set is necessarily contains necessarily the essential set. So in the minimal covering set, you have at least A, B, C, D, and E. The question is whether F is also in the minimal covering set or not. So for that, we need to have a look. If we add F to A, B, C, D, and E, is F a covered solution? So it's not covered by A, B, C, and D because they do not win against A, whereas F does win against A. And it's not covered by E because it wins against D, and E is not able to win against D. So F, in fact, is not a covered solution. So here, in fact, we have an example where the essential set is A, B, C, D, E, and the minimal covering set, in fact, is everybody. So, which proves that sometimes the essential set is smaller. It's quite easy to prove that the essential set is included in the minimal covering set, but this example proves that the inclusion can be straight. And the essential set also has all the nice properties that we expect, so that's wonderful. Yes, something I wanted to stress is that, so just for as a reminder, the essential set is always included in the minimal covering set. The minimal covering set is always included in the iteration of removing the cover candidate, which is itself included in just removing the cover candidate once. And all this is, I have not written it here, but all this is included in the top cycle. So the essential set is the finest solution that we have amongst, let's say, the reasonable solutions. Yes, Remy?
Complexity-wise, computing those sets, is that easy or not?
The essential set?
And
The essential set, it's you do it by a complex optimization, so it's relatively quick.
there's no, like, will you have easily understandable algorithms where you can say to somebody, I computed it this way?
No, you always do it by complex optimization. Yeah. So just for the takeaways of this talk, what is a tournament? So a complete antisymmetric and irreflexive relation. A tournament solution is a procedure, an algorithm to select a subset of best candidates, and there is a typo here, of best candidates. And when you interpret the matrix of the tournament as a two-player game, then it leads to very interesting tournament solutions, and in particular the minimal covering set and the essential set, because both of them have very appealing axiomatic properties like monotonicity and stability by removing the losers and so on. But knowing also that the essential set is a bit finer, so in some situations you will select a smaller set of winners, which is generally what you want. And thank you very much for your attention. Oui, Emma. Yes.
So would it make sense here to choose a solution that uses this, but only choose the candidates that have the highest probability?
Yes, you can do that, and in fact, yeah, it's suggested in some papers of the literature. But the problem, if you do that, is that you will have very few axiomatic properties. In fact. As you would expect. Yes.
No, there is something in the chat.
Something in the chat. Okay, so I don't know if so the question of Marco Olivier is are there natural extensions where relation orders are stochastic, or when you have multiple order strategies to decide, e.g. Magic the Gathering? Okay, so two parts of the question. So the first part is that when you have a deterministic game, a two-player deterministic game, and typically a zero sum in the sense that either one of the player wins or it's the other player who wins, you can also always write it in a normalized form, where in fact you will list all the strategies. And for example, in chess, a strategy would be a complete algorithm that would say in any situation what you will do. That's a strategy. And in principle, you could write a very, very, very big matrix with all these possible deterministic playing algorithm, and write the matrix of the game to say, okay, this strategy wins against this one, this one wins against this one, and so on. So when you have a deterministic game, in fact, you can always write it in this normalized form. And for the other question, I don't know if I understand it correctly, but if it amounts to saying that between one candidate and another, you don't have a clear victory, but you can have a probability of victory, for example, or an intensity of victory. So in fact, there is a very, very natural extension. So in voting, for example, imagine that for each pairwise comparison, not only do you know if candidate A is preferred by a majority of voters, but you know the tally. You know that, for example, 70 voters preferred candidate A and only 30 preferred candidate B. Okay. Then you can write a game with this matrix. You can say, okay, let's play the game of the candidates again with Remy. I can choose a candidate to choose one. And if I choose candidate A and you choose candidate B, then I will gain $70 and you will gain $30. Okay. And we can do exactly the same. We can compute the optimal strategies of this game. And we can take the support of the optimal strategy, which is all the candidates that come with non-zero probability in the optimal strategy. in fact, this solution, which is a generalization of the essential set to weighted tournaments, has very similar properties to the essential set. It has essentially all the good properties of the essential set. So yes, it generalized to weighted tournaments.
This is very specific to this game.
Okay, so here you have a particular kind of game, which is game with a temporal element. So while it's true that you can always put it as a normalized form with a big adjacency matrix and so on, you also have particular notions of strategy and equilibrium in that case. And for example, you have perfect subgame equilibria, for example, but we can discuss that later.